Hello and welcome to the webinar, Grid of the Future, Lifetime Costs of Energy Storage Technologies. My name is Chris Robinson. I'm a Senior Director here at Lux Research, and I'll be moderating today's session. Presenting today is my colleague Chloe Herrera, an analyst here at Lux. Throughout the webinar, you can type any questions you have into the questions box on your screen. Time permitting, we'll answer all the questions that we can. If your question doesn't get answered, please don't hesitate to email it to questions@luxresearchinc.com, and we'll make sure to respond. Let's jump into the presentation. Over to you, Chloe.
Thanks, Chris. So today we'll be talking about long-duration energy storage technologies and really what their role is in the future. And first, I'm going to be starting off talking to you about what the actual role of energy storage is and why we really do need it. But first, I want to talk about a specific instance. So in 2021, a couple years back, there was a severe winter storm in Texas. During this storm, Storm Uri, the temperature dipped down to negative 19 degrees Celsius. And in the power sector, the winter storm had some pretty extreme effects. There was surging demand for power due to increased heating, power plants were disrupted, and the industry across the state also halted their operations. This storm created massive outages with up to 70% of residents losing power. And these outages had a detrimental effect to the economy of the state. In fact, the Electric Reliability Council of Texas predicted that the outages cost them billions of dollars. During this time, the price of wholesale electricity jumped all the way to $9,000 per megawatt hour, which is up from an average of about $50 per megawatt hour. And if you look at this plot on the right, which is the outages by cause, there's on February 15th, about 30 gigawatts of outages were weather related. This is including frozen infrastructure or other cascading effects associated with that. And what we observed is that from all of these outages, there was one particular piece of the power puzzle that was missing. And energy storage would have significantly improved the reliability of the grid during this time. Of course, there's multiple ways outages could have been avoided, but energy storage was a major untapped resource that could have played a critical role here. At the time, Texas had less than 1 gigawatt of energy storage across the whole state. Now, this might seem like an extreme example, but we're seeing more and more of these weather-related incidences become more frequent, and we expect to see this to continue in the future, not just for the winter, but also for extreme summer events as well. Now, if we look outside of extreme events, how else can energy storage play a role? Now, if we think about the increasing role of intermittent renewables, we also see that they challenge reliability every day. So this plot shows 24 hours of data in California with the demand curve as well as the renewable supply. And what's notable here is that the two peaks do not correspond to peak supply by solar. And if California is depending primarily on solar, there's going to be a lot of gaps in terms of this supply and demand. And energy storage can play a huge role here in being able to keep the electricity system stable and operational. One particular application here is ancillary services like voltage regulation and frequency control. And energy storage can provide these really quick responses with a very high efficiency needed to keep the grid running. One other notable aspect here is peaking capacity. So like I mentioned earlier, you're not seeing that renewables output during the time when it's most needed. And in this case, energy storage would be able to provide that peaking capacity by taking solar energy when it's at its highest and just displacing it to these peaks. And then finally, what you'll notice here is that as peak demand starts increasing, the actual solar output starts decreasing. And so energy storage would be used then to pick up that loss in solar to match the curve of demand for power. Now, across all of these applications, the requirements are very different. So for ancillary services, like I mentioned, you need a high efficiency, but maybe for longer duration applications, you don't necessarily need as quick response if it's a very reliable curve, and you might not necessarily need those high efficiencies. And that's really where technology diversity and energy storage becomes really important. So we categorize energy storage into 5 different buckets. The first is going to be closed electrochemical systems. This is going to be technologies like lithium ion, sodium ion, zinc ion, things like that. And this technology is really categorized by high efficiencies, typically around like 85% or higher, and a more compact design than other technologies that allows for more modularity. And the technology, while it does have these positive aspects, it tends to be limited by cycle life and operating environment. So if you think about a lithium-ion battery, there's a relatively narrow operating temperature window. Next is redox flow batteries. And this is going to be technologies like vanadium redox flow, iron flow, zinc bromine, and then even like organic flow batteries. Now, these technologies are preferred over lithium ion batteries in instances where you might want to decouple your power and energy. So say you want to have a very long duration application, you can just add more electrolyte to your flow battery. But the disadvantage of flow batteries is that they tend to have really low energy densities. So this technology isn't going to be the best fit in areas that have space constraints. And then rounding out the electrochemical technologies is metal air batteries. So the most prevalent for stationary storage are going to be iron air and zinc air, where the reason that companies are looking to adopt this technology is that they tend to have very low cost materials, especially compared to some of these more close electrochemical systems. But the major disadvantage here is that they tend to have a limited cycle life and lower efficiencies, around 60 to 70%. Then we can get into the mechanical energy storage technologies, first being compressed or liquefied air. So this can include compressed air energy storage, cryogenic liquefied air, and liquefied CO2. Now, these technologies are advantageous because they tend to have very long system lifetimes, and they can discharge to 100% depth of discharge. Now, the major disadvantage here is that these systems tend to have a pretty slow response rate, especially compared to electrochemical systems, and they also tend to be pretty CapEx intensive. And then finally is pumped hydro. Now, this is the most mature and most deployed energy storage technology, but it tends to be geographically limited. There's very few available spots to incorporate pumped hydro, but it can be very economical at high scales, and it tends to have a pretty high efficiency. But with all of these technologies, then the question comes is, how do you actually choose these technologies? And what we find is that project developers are really fighting between technology and economics of these different technologies to understand which to deploy. On the technology side, technology maturity and deployment history are really big drivers for adoption. So that's why we're seeing mostly lithium ion being deployed in recent history. But on the technology side as well, application fit is really important. So how well can your technology actually fulfill the role that is needed? Then on the economic side is the levelized cost of storage, which is the lifetime costs of these technologies, then the upfront costs, and then also the revenue potential. So can the energy storage asset not just participate in the original application, but are there other ways that it can receive revenue? But we at Lux think that the levelized cost of storage is the best way to compare multiple technologies. And the reason for this is that if you look at the levelized cost of storage, it has a much more holistic view of these technologies and the technologies in the application that they're looking to serve. So Lux has built its own levelized cost of storage model, where for each LCOS analysis we do, it includes both the system inputs, operational inputs, and financial inputs. So the actual application the energy storage system is serving, but also technology inputs. So for each technology, we consider the capital cost, efficiency, O&M costs, and replacement costs. So coming up next, I really want to present this levelized cost of storage analysis to show that in different applications, there's going to be a variety of technologies that are best fit. And in order to really show this, I want to present 4 of the technologies that we think have, or 4 of the applications that we think have the highest potential for growth. So for the most part, energy storage has primarily served a lot of ancillary services and potentially some backup applications. But in the future, we really expect peaking capacity, renewables integration, renewables backup, and microgrids to be fast-growing applications for energy storage technologies. And first, we will look at peaking capacity. So for peaking capacity, it's one of the shorter duration applications here, usually around 2 to 8 hours, and it can be around 100 megawatts. And peaking capacity is mostly used for managing this unexpected demand at times of peak use. For our LCOS analysis, we expected a 100 megawatt system with a 4-hour discharge at 120 cycles per year. And what we found is that even at large scale and low utilization, lithium ion is actually the best choice in terms of LCOS. Now, you could potentially look at other technologies, but what really drives the lowest LCOS here is the high efficiencies and the cycles per year, which allows for lithium ion batteries, for example, that might have limited cycle life to have a longer lifetime before you have to augment. And now we can look at microgrids. So microgrids are mostly behind the meter asset where it can either be islanded, so completely separate from the grid, or grid connected. And we're actually seeing an increase in these grid connected microgrids that increase reliability for utilities customers. And microgrid applications in energy storage tend to be around 8 to 16 hours, but they're also a smaller system size between 1 to 10 megawatts. And looking at the LCOS analysis, we find that flow batteries are really best suited for microgrids. In this analysis, we looked at microgrids that were 1 megawatt with a 16-hour discharge that run every day. So you can imagine a renewable generation happening for about 8 hours, and then the energy storage asset running for the remainder. And flow batteries are really the lowest cost here because of this frequent cycling. Lithium ion is competitive because it tends to have a higher efficiency, but at the end of the day, especially at these smaller scales, vanadium redox and potentially even zinc bromine are going to be really good options for this application. Now, looking a little bit further into the future are two applications really reliant on renewables deployment. The first is renewables integration. Now, this is primarily going to be an energy storage application that works really closely with renewables output, where as, say, a solar plant, for example, might have a cloud pass over it, an energy storage asset would pick up for the loss of output. And this can be for discharge durations between 8 to 24 hours, depending on the renewables makeup of the grid. And they're going to be much larger system sizes. And as we look at energy storage technologies that can address this variability, the system is going to be 100 megawatts, 6-hour discharge, and discharging every day. And what we find is that really the technology choice here is going to depend on what the project is and where it's situated. So, for example, pumped hydro is going to be the lowest cost technology here. But as I mentioned earlier, pumped hydro has relatively limited available sites for project development. And then the second lowest levelized cost of storage technology is compressed air energy storage. Now, compressed air energy storage, especially if you're looking at underground cavern storage, is again more geographically limited. There's going to be a very extensive site selection process to incorporate compressed air energy storage into the grid. So it'll really just depend on the different needs and requirements of the specific application. Now, finally is renewables backup, which we would consider a much more future application for energy storage, which is where you need much longer discharge durations, around 32 hours to 256 hours. So it's multi-day, potentially even multi-week energy storage at these really large system sizes. And this is really going to become critical as we have more and more intermittent renewables on the grid, and you need more of like a much longer duration backup for that. And in our LCOS analysis, we examined a 100 megawatt, 72-hour system that discharges about every week. And we found that for renewables backup, large-scale storage, mechanical energy storage is really going to be the best fit here. And the primary reason is that it scales really well, especially at these larger system sizes, and there's less focus on high efficiencies for these longer duration applications. And so now that we've explored the different levelized cost of storage situations, and you've seen that different technologies are really going to fit different applications, let's talk about the strategies that we can employ with energy storage. And so bringing this back to really this choice that developers need to go through, it's not just about this LCOS. The LCOS is a great tool to understanding how you can start comparing these different technologies, but it's really going to be one piece of the puzzle. So again, technology maturity and deployment history are going to be one of the bigger factors in terms of technology adoption, especially as utilities are learning how to deploy new energy storage technologies. but LCOS is a great economic tool to understand these lifetime costs. And one thing that you might have noticed is that in our LCOS analysis, we found that there's really 3 key technologies in the long duration landscape. The first is going to be closed electrochemical systems. And if you're looking at other closed electrochemical systems besides lithium ion, really the emphasis should be on high efficiencies and low capex. The technologies in this category really need to compete with lithium ion batteries for their cost and their performance. And then second is redox flow batteries. The most popular, of course, being vanadium redox flow. But here, redox flow batteries are going to be really valued for their decoupling of power and energy. In fact, many utilities quote this as the main deciding factor between closed electrochemical and redox flow. And then third is compressed or liquefied air. And really, this is about these large-scale mechanical energy storage systems when you need bulk energy storage. And in this category, the main considerations here are finding a technology that scales really well with size and decreasing costs. Now, Texas, if we bring it back to the original story about Winter Storm Uri, Texas is still experiencing extreme weather. In fact, just earlier in January, they had all-time peak demand. So the only difference here is that actually Texas has added storage. So since 2021, there's been a boom in the energy storage landscape in Texas. In fact, 7.5 gigawatts of storage is expected to be added just this year. And not only is Texas looking at shorter duration lithium ion batteries, but they're also investing in potentially creating compressed air energy storage systems as well. So the state is increasing its diversity in energy storage technologies to build this more reliable and resilient grid. And so how do we start building strategies around energy storage? The first thing to keep in mind is that grid needs are really going to depend on what the local energy makeup is. So each grid is going to be different, and it's going to utilize energy storage differently. So depending on what types of renewables, how many renewables, and how quickly you're going to integrate those into the grid are going to be factors in terms of what kinds of applications you need. And this growth that I mentioned in these 4 applications is really going to vary across different grids. The second is that energy storage is really going to depend on each technology developer's strengths. But one way to really push new technologies forward is to utilize government funding. And if you're a commercial operator looking to decarbonize your operations, this is a great space to start acting as a pilot case, looking at how you can incorporate longer duration energy storage. And this can potentially prove use cases as these technology developers start looking at utilities that want this longer duration technology. And for equipment or material suppliers, the newer energy storage technologies is a great opportunity to start paving the way for lower cost technology. So being able to provide materials for electrochemical technologies or equipment to help scale these technologies in a cost-effective manner. And so I'll leave you here with 3 major takeaways. And the first is that LCOS is really going to dominate technology choice. It's a great tool to use to understand the lifetime costs of different technologies in a specific application. But that's not the only tool you can use, and other factors will continue to be important. So things like environment, energy needs, renewables, and technology maturity are all going to influence this choice. The second is that there's a lot of different energy storage categories, but according to our LCOS analysis, there's really only 3 categories that are going to be the winning technologies. And all 3 of these categories require innovation. And this innovation really should be focused on lowering costs so that these technologies are more adoptable. And then last is that long duration energy storage pilots are really going to be critical to increase this application adoption. We're seeing that grids are already incorporating large amounts of intermittent renewables, and they're starting to need these longer duration energy storage technologies. But over the next few years, these pilots are really going to be key in determining how utilities and how other operators are going to be able to incorporate energy storage into their plan. So thank you for your time.
Yes, and thank you, Chloe. So now I'll be taking questions that you might have in the presentation. So reminder, you can pop those in the questions box. And if we don't get to them, someone from Lex will be in touch after the webinar. We have one coming in, so keep sending those in. But the first one's on sodium ion. So we did talk a little bit about sodium ion. And the question is, how do you see sodium ion fitting into this picture? Will it displace lithium ion?
Yeah, so like I mentioned in my review of the 3 major technology categories, sodium ion falls under that closed electrochemical systems. And the major barrier in other technologies eclipsing lithium ion is really the cost. Sodium ion has potentially a very low cost. In fact, I've seen developers in China targeting $50 per kilowatt hour for cells, which is much, much lower than lithium ion. Of course, you're going to take a hit in efficiency and potentially cycle life, but with such low capital costs for the cells, you're going to have a much lower LCOS. So I think there's a lot of potential for sodium ion batteries and stationary storage, and it can potentially displace a lot of this lithium ion deployment, but it'll be much further into the future.
Understood. And the next one is around metal air, which I don't think is too surprising given the noise that companies like Form Energy have made in the space. But we're not so bullish on metal air. So why don't you think metal air batteries are considered a winning technology per se?
Yeah, so metal air batteries were never the lowest LCOS across any of the applications that we looked at. And the reason for this is because we just haven't seen enough scalability in this technology. So although it is made of low cost materials, there aren't enough use cases right now for, say, 100 hours of storage. So costs are still relatively high. I know Form Energy is promising $100 per kilowatt hour or even lower, but we still really haven't seen concrete numbers here that really make us excited about the technology.
Yeah, I think Form Energy is down as 20 per kilowatt hour, but I think the point still stands. We haven't seen too much information from them on that. Mm-hmm. And the last question I think is a really good one to wrap up on, which is really about timing. So when do you expect to see significant need for more than 16 hours of storage, for example?
I think that once we get into those very long duration applications, you're really not going to see significant deployment probably past 2030. And like I mentioned earlier, it's really going to depend on the energy system. So what are the grid needs? I suspect that not all grids are going to need 16 hours of energy storage, but the ones that do might need a significant amount or maybe just a little bit. But I still think we're about a decade away from that.
Mm-hmm. Excellent. Well, thank you very much once again, Chloe, and that concludes our webinar for today. So the presentation and the recording from this webinar will be sent to all attendees via email, so keep an eye out for that later today. After leaving, you'll be prompted to complete a survey in today's presentation. We do appreciate any feedback you might have. It helps inform us and improve future webinars. And finally, take a moment and check out our upcoming webinars. So thanks for joining us and have a great day.
Thank you.